Welcome back. In the last class, we started discussing about processing of NMR time domain data. We discussed at stretch, a lot of discussion took place about Fourier transformation, what happened to this time domain signal, resolving them into mx and my components, and then finally we introduced the decaying function, and then we also brought in the phase component, which there will be phase errors when the real and imaginary components are not exactly out of phase by 90 degrees. Varieties of things we discussed. We discussed about a lot of Fourier transformation functions also. Now continue with the phase correction. We saw there are phase errors. We also discussed why it comes. We said when they are not exactly out of phase, real and imaginary parts, we are going to get different types of phase errors in the signal. It can even be negative absorption to positive absorption. The angle from minus 80 to, for example, in this case, minus 180 to plus 180, the phase errors can go all along. Okay, let us continue with this phase correction today. And this expression we wrote, this was my original signal, and this is the decaying function, and we incorporated this phase error, assuming there is an error of phase by an angle phi. Now what I want to know is, I will incorporate another function phi, which is a corrective function, so that this has to correct this error. Okay, the main signal which we collected ST, this was there. Now I multiply this time domain signal by another phi corrective function, which is also exponential on both sides. Now I can correct the phase such that we get pure absorptive spectrum in the real part for the entire region of the spectrum. Remember, when I take exponential A and exponential B, which is translates to exponential A plus B, that is a mathematical operation. I don't want to go into too many basics, you should understand that. Now take this exponential function, exponential of I phi correction into time domain function. If you take our exponential of I phi into corrective function into this one, and I retain this part as it is. Now what I have to do? If I have to make the corrective function, if my corrective function is exactly equal to minus of 5, then what happens? This term goes to 0, then it will be 1. So there won't be any phase error at all. So that is a very important thing. If I set the phase correction to minus 5, then the exponential function will be 1. So that means there won't be any phase error at all. You get a signal in the after Fourier transformation. You will see only pure absorptive spectrum in the frequency domain. That's what I have to do. So my job is to find out what is this function, right? This gives a spectrum now without phase error, and the real part corresponds to the pure absorptive spectrum. Now, this is what we did in the time domain. You can do that. Multiplication by an error function like this to see that phase errors are nullified. The same thing you can do phase correction in the frequency domain also, because we do not know what are the phase errors in the time domain. So many signals are there overlapped with, there is an interferogram. We do not know how to correct that, but we can do the correction in the frequency domain spectrum. So we can do the correction like this, incorporate the correction factor for the phase in the frequency domain also. So this is called frequency independent or zero order phase correction. I can do that. A one factor I incorporate, and I ensure that I can correct for the entire frequency. This is called entire spectrum. I can make the phase correction. This is a frequency independent, also called zero order phase correction. Okay. You can do this manually. You can keep on, sit on the spectrometer. You can vary the angle between real and imaginary parts such that you can correct it. And you can correct the phase and make it perfect. Of course, in the present day spectrometers, you don't have to do anything. Human intervention can be minimized quite a bit. You can do it automatically also. But remember, this correction factor which I'm introducing is frequency independent. Of course, there is another type of error also called frequency dependent phase error. We saw that as we went from one end to other end, different peaks will have a different frequency. I showed as a function of the angle, from minus 180 to plus 180, there can be phase error. In addition to that, you can see that different frequencies in the same spectrum can have different types of phase errors. See here, this is one type of phase error. This is another type. This is another type. This is called frequency dependent phase errors. So this is called frequency dependent phase errors. So I can correct that also, and then finally ensure that all peaks in the spectrum are pure absorptive like this. That can be done. Okay. Look at the spectrum. This is the type of spectrum you are going to see. This is without phase correction. This is after phase correction. I'm sorry, not with. This is without. There's a mistake. It's the typo. I'm sorry about it. You read it as without phase error. Oh, I'm sorry. Not with phase error. I agree. Not without phase correction. It is with phase error. Okay. There is error incorporated here. When there is a phase error, you see like this. It is correct. No doubt about it. It is correct. Now, after I incorporated the phase correction, this is the type of spectrum you see. Look at the baselines here. Every peak here, there is one type of phase error. This is one type of phase error. They are really opposite phase errors here. Okay. But now, after phase correction, we get a fantastic spectrum like this. Very beautiful spectrum. Very beautiful spectrum. This is what is called phase corrected spectrum. Please remember, you should know how to do the phase correction. While processing the data, we can play with the time domain signal in various possible ways. We can apply certain type of window functions. What are these window functions? Why it is beneficial? Let us see that now. Let us say I have a frequency, I am a time domain signal which is decaying with an exponential like this, which you worked out. Exponentially decaying signal. I do the Fourier transformation. I am going to get a Lorentzian like this with the line broadening, which is full width at half maximum, which is equal to inverse of this. Why? But one important theorem is there in Fourier transformation. It is called convolution theorem. What convolution theorem says is multiplication of time domain signal by an exponential correspond to convolution in the frequency domain. This theorem is called convolution theorem in Fourier transformation. Remember, I can multiply two exponentials in the time domain. No problem. It is possible. Then it convolutes in the frequency domain. Okay. So in which case, I can understand lot more things. I can do many more things with the time domain data. So these functions I can use. These are called apodization functions. For example, I have a time domain signal, frequency domain signal here. I am going to get multiplication by something, and this is the real frequency spectrum. And in practice, you can multiply this in the time domain and get the frequency domain spectrum like this. This is what is called multiplication in the time domain. This is called a convoluting function. These two functions are convoluted. And this convoluting function here, this is called a window function. Okay. I can use this window function for various purposes. And there are several such window functions. It could be exponential decaying function, exponential increasing function, trapezoidal function, Gaussian function, varieties of function you can think of. These are all called window functions. I can multiply the free induction decay time domain signal with these functions, and afterwards I do the Fourier transformation. The effect of it is seen in the frequency domain spectrum. Okay. Now, where I use is, you can make it can be clear for you from this type of FID. You see, this most major portion of this FID, which is containing the signal, is here. This is where the signal lies. Lot of signals are there. But here, mostly it is noise. Okay. Now, if I collect the signal for a longer duration, I told you how to optimize the spectral width in the previous 1 or 2 classes. There is no need to collect the signal for infinite time because you will be collecting only noise. And you cannot also cut the FID like this. You'll be truncating, giving rise to sync artifacts in the frequency domain. So you should have optimum. But anyway, you also have to have the very good digital resolution. Many parameters you have to optimize. Let us say you have collected the signal. But still, after acquiring the signal, you can play with it. We can use a window function to remove this noise component at the end. How we do it? Let us say I am going to take a exponential function, keep decaying like this. See, decays like this. Then what happens? Initial portion of the FID is retained, and as you keep going far away, this signal, as you keep going far away, this big signal decays. So that means if I multiply like this, here afterwards, I can completely remove the noise part. Here afterwards, I completely remove the noise part because I can multiply the time domain signal by an exponentially decaying signal. What is the advantage of that? Remember, we are multiplying two exponentials. As I said, these two like exponentially a plus b. I showed in one of the slides. That means you are adding the line width. If I multiply by a function, let us say this is called a line broadening function. If the line broadening function is 1 hertz, what does it mean? The entire spectrum in your this thing, all the peaks of your spectrum, you are increasing the line width by 1 hertz. Let us say I have 100 peaks, or let us say I have 20 peaks. Each peak has its own natural line width. Now, you are multiplying by the window function, which is exponentially decaying with, let us say, 1 hertz. Then what happens? Every peak will get broadened, the width will be increased by 1 hertz. Fine. But advantage is you have reduced the noise component here. Noise part is removed. So what is the benefit and what is the loss? The benefit is you will get better signal to noise ratio because noise part is reduced. But loss is you are incorporating the line width into the peaks. You are incorporating artificially line width into the peaks. So there is a benefit and there is also a loss. Look at the signal, it is a raw FID, mostly noise here, nothing else. Now multiply by an exponential function of, let us say, 1 hertz, or you can choose anything depending upon how much FID you want to cut it. Now, if you product of this thing, if you take in the time domain, do the Fourier transformation, you see completely you remove the noise in the part of the noise in the frequency domain and increase the peaks by 1 hertz. Look at this one. This is a classic example. You can see this is an exponentially decaying signal and line width is exponential function is 0.2 hertz. If you do that for this signal, you are going to get a peak like this. Same, multiply by 0.5. This is a real time domain signal, it is truncated. Multiply by 0.2 hertz, you get a peak like this with a certain line width. The same signal multiplied by 0.5 hertz. See, the signal to noise ratio is better, but you don't see it here. Of course, you can see here to here. Here there are artifacts. Carefully, you see it because FID is not completely decayed; it is truncated. But here you see, noise is better, but line width is broader here. This is a sharp peak. This is a broad peak. Okay, we go by multiplication factor of 1 hertz. See, FID decays even faster. You see, if the FID decays, longer the time it decays in the time domain, sharper the signal in the frequency domain. That statement of mine, please don't forget. I've been telling you. So now with the line broadening function of 1 hertz, it decays even faster here compared to this. As a consequence, this line width is even more compared to this. You see the advantage of the exponential function. You can use exponential function as a window function, multiply the time domain by this, by certain value, and appropriately choose so that you can reduce the noise component, increase the signal to noise ratio. At the same time, you should not enormously broaden all the peak. Supposing I use instead of 1 hertz, 100 hertz, you will not see signal at all. You get a broad hump like this with 100 hertz line width. Okay, like this. This width is 100 hertz. So you have to judiciously decide what you want. This tells you what is the advantage of signal to noise ratio. Now, in the window function with 1 hertz, and this is no window function, this is with window function of 1 hertz. Look at this one. Line width here is 1 hertz without any window function. Now, with the window function, line width become 1 plus 1 because you added 1 hertz here, line width become 2 hertz. This was a natural line width, 1 hertz. You did not do any window functioning, no artificial processing here. But after multiplication of the free induction decay by an exponential function of 1 hertz, the line width became 2 hertz here. But look at the signal to noise ratio. There was more noise here, signal to noise ratio. This is the Fourier transform signal of this one. See the noise here. Signal height is here. Lot of noise is present. You calculate signal to noise ratio. You will get, it is turning out to be 28 approximately. Now after exponential multiplication, though you have brought in the line width, look at the signal to noise ratio, which is much better. It's almost double. Of course, you cannot do this if you have, let us say, 2 frequencies separated by 1 hertz. Then if you use a line broadening of 1 hertz or 2 hertz, they will get merged. The resolution will go bad. So you have to play with the resolution and the signal to noise ratio accordingly. So you have to properly choose the window function based on what your requirement. Is it clear? So point is, the take home message is, the window function exponential if you use with a certain multiplication factor, it will give rise to line broadening with the benefit of better signal to noise ratio, but with a penalty of losing the resolution. These are the points which you must remember. So look at this one, how the sensitivity gain is there. But you may ask me a question, why should I use a positive function if I use the LB line broadening function negative? Interesting thing what happens is, it will become sharper than this. The line width will be reduced. But signal to noise ratio become much more than this. Look at this one. This is an example of a situation. This is a realistic FID which I showed you. Multiplication by a line broadening function of nearly 5 hertz. Fantastic. You removed better signal to noise ratio is there. And each peak, of course, it is increased in the line width compared to natural line width by 5 hertz. Every peak, line width is increased by 5 hertz. On the other hand, multiply by a negative line broadening function, exponential function, negative. Look at it. Signal to noise ratio, the noise component is increased in the FID part. Here, noise component is completely reduced when you use positive FID and positive EM, exponential multiplication. In the negative exponential multiplication, you have enhanced the noise component here, noise part. Look at it. When you do the Fourier transformation, you get bad signal to noise ratio. The signal to noise ratio reduced here. But as a benefit, your line width will increase. Line width will decrease quite a bit. Your resolution has improved. That is an advantage. So you have to understand what you require. Whether you want signal to noise ratio like this, by reducing the noise part of this FID, or you want a better resolution by increasing the noise part of the FID. Depending upon that, you can use exponential multiplication factor, which is called a window function, either with a positive value or a negative value. But remember, these are all within 1 hertz or 0.5 hertz, 2 hertz. You can't use large value. Then you completely submerge all the resolution. If the 10 peaks are there which are resolved, everything will go. If you use, let's say, 50 hertz line width, you'll get a broad hum, nothing else you will see. So you have to judiciously decide. So you can use different types of window functions are available. You can have the window function. If I take a raw free induction decay like this, without any window function, we have what is called a Gaussian window function, unshifted sine well. This is exponential multiplication, shifted sine well, trapezoidal function. Number of window functions are there. Okay, I have no time to discuss each and every one of them. It will take enormous amount of time. But I'm showing you the effect of multiplication of each of them and the free induction decay, raw free induction decay, how the FID gets affected. Look at this one. This is a Gaussian. Now the signal part here increased, you reduce the noise here. Here signal part is more in the shifted sine wave, whereas here in the unshifted sine wave, here the noise component is quite a bit reduced, but signal is also decaying. If you use exponential multiplication, you will reduce the noise part here, but you are increasing the signal line width because signal is decaying very fast. You can see the effect of all those things here. There is no signal, no window function, no line broadening, nothing. Let us say natural line width 1 hertz. If we use a Gaussian, I can bring down the line width. Okay, you see the line shape is much better. I can use sine wave. I can bring down the line width little bit better, even now, much better. See, compared to this is a better peak, sharper peak. But look at the baseline, it gets distorted. I can use the exponential function, but you see, you are increasing the line width, beautiful signal to noise ratio, but line shape is also not distorted. So there are different window functions. Based on the window types of window functions you use, we have different effects seen on the frequency domain spectrum. You can have a distorted phase, you can have signal to noise ratio more, or you can reduce the signal to noise ratio. Your line width will become better, or line width will become bad. Varieties of things you can think of. Take for example, it is in the case of FID, I gave you, sometimes this is a real free induction decay which is truncated, and you see the distorted line shape here, especially at the bottom. Like a sinc function artifact you are getting, because it is going to be a truncated FID here. It is not allowed to decay completely. But you see, at the bottom you have sinc function artifacts. Whereas, if I multiply by this one, you remove the sinc function artifacts. So you have to properly decide, looking at your spectrum, what window functions you have to use. Mind you, you can do this after acquiring the data. So you have enormous time to play with these functions. You can use trapezoidal window, and this is the signal after Fourier transformation. But after using the trapezoidal window, lines become better. But you see, this baseline distortion sometimes will not disappear. Same way, Gaussian window, see much better. This distortion removed, line shape becomes mixture of Lorentzian and Gaussian here. Because NMR spectrum is a Lorentzian, you are multiplying by a Gaussian, the line shape is not pure Lorentzian, it is a mixture of Gaussian and Lorentzian. Okay? You can have a shifted sine wave like this, shifted Gaussian window like this, and now you get sharp peaks, you see. It yields increased resolution, but lot of artifacts in the base. Whatever the artifacts which we already had here, because of truncated FID, instead of removing, we are adding more artifacts at the base. Take an example of a sine window. It's another window function. It is a sine window like this. This is called a sine window. See, much better resolution, but more sinc function signals, sinc function artifacts are much more stronger than the normal one. Okay. Shifted sine window is much better. You get better resolution. It suppresses artifacts, okay, and get a better quality spectrum with a feature is much better than this, you see. This type of distortions are not there. You get good quality spectrum by using shifted sine window as this thing. So these are all some of the important points which I wanted to tell you as far as window functions are concerned for processing the data. But remember, there are so many window functions. You can play with it, if you play with it with your time domain data to get a very good signal with a good signal to noise ratio and proper resolution. The choice is in your hands. Okay, I gave you many examples, many types of window functions we can utilize. Now I will come out with another important application, another parameter which we can play with in the time domain signal called zero filling. What is this zero filling? FID is digitized signal and has a number of data points. We saw that free induction decay is nothing but the series of data points which is digitized and collected. We saw that early in one of the examples. And now what I will do is I'll take the free induction decay and add equal number of zeros to it. Let us say I collect 8K data points, 8,000 data points digitized. At the end, I add 8,000 data points with zero interest, zero signal, like a noise, no signal at all, but no noise at all. I simply add zeros. What did I do? I increased the data size from 8K to 16K. What is the benefit? Please remember, I discussed this for digital resolution. I wanted to tell you what is the digital resolution dwell time. If the more number of data points are there, see, as the number of data points increase, the dwell time becomes smaller and smaller. Smaller the dwell time, you can digitize the signal. Okay, you can sample with each frequency more number of times, and you can get better resolution. All the if there are frequencies which are closely spaced like 1 hertz or less than that, you can resolve by sampling at closely spaced points. So the dwell time can become smaller. What is the advantage? We get better resolution. So that is another point important you should see. Zero filling is important. You can add zeros at the end of the FID, regular FID, to double the size of the data, which will bring down the dwell time, enhances the resolution. Look at this one. This is a free induction decay. Now at the end of this, same size of the time domain is added here with zeros. Let us say this is 8K data. Now I add 8K zeros. It will become 16K data. Now these are the time domain points digitized. Now look at it, it's much better. To make it even better, add one more time. Okay, this was 8K, make it 16K or even 32K, or doesn't matter. Add few more data points. Then you see the digitization points. Remember, I showed this as the number of points, digitization points increases, and the dwell times, when you reduce it, you get better resolution. We saw that a peak which is unresolved of 6.3 hertz line width, finally we brought down to 0.10 hertz. Remember, 0.1 hertz by increasing the time domain points. This is analogous to zero filling. There, literally, you can increase the time domain point. If you cannot increase the time domain point, at the time of processing, you can add zero at the end. Why? Because if you increase the time domain points in the real time of, at the time of acquisition of data, your acquisition time increases. You have to acquire the data for a longer time. You don't need to do that. If your FID has died down like this, you acquire data up to this, only for this much time. Rest you add zeros. This is also faster way and better way also. Okay. This is another point to play with the time domain data. You can judiciously decide what you want to do. Okay, next is I want to tell you something about resolution and peak test. I do all sorts of tuning, shimming, everything. I get a peak. But how do I know I have got a very good resolution and my peak shape is correct? Now, not only you should get a resolved peak, you must get a perfect peak shape like a Lorentzian. If I get a peak like this, you may resolve the peaks, but you see the shape, that's not good. So you must choose, you must optimize the parameters such that your resolution should be better and your peak shape should be proper. For that, in the good old days, people were using what is called orthodichlorobenzene. At a lower frequency spectrometers like 300 or 400, it was an AA prime BB prime pin system strongly coupled, giving 24 peaks. The challenging task was to tune the homogeneity to resolve all 24 peaks. That used to give you better resolution. But nowadays that is outdated. People use recommended is what is called peak shape test and resolution test are done with 3% CHCl3 in acetone DC. Take a proton spectrum of chloroform, you'll get a single peak. Now measure the peak width at a half height. There are three things you have to do. Okay. Peak height, peak width you have to measure at half height, full width at half maximum. And then you increase the signal intensity enormously. Find out 0.55% of this signal intensity at the bottom. Okay. And then 0.11% of that at the bottom and measure the line width at 0.55% of at the bottom where you are going to get carbon 13 satellite. Why it was chosen 0.55% is if a CaCl3 is seen, there is a peak here, you have carbon 13 satellites here. Carbon is 1% abundant. So the intensity is divided into two. This is 0.5, this is 0.5 intensity. Because it's 1.1%, it's written 0.55 here, 0.55 here. No problem. I always take 0.5% for approximate value, no problem. And at this height, at the height of the satellites, you have to measure the line width. Peak height is at the full width at half maxima. Measure the line width. Measure the line width at the height of the carbon 13 satellites. And then again for increased intensity further. Measure the line width of this at 0.11% of this height. Then what happens? If there are certain specifications for that. If the specifications matches with the recommended line width, then your resolution is very good and your peak shape is also very good. For example, it is like this. I'll give you an example like this. If I measure at the height of the satellite, enhance the main peak and measure the line width, it should be 13.5 times the natural line width. 13.5 times. For example, my CaCl3 line width is, let's say, 1 hertz. Maybe a bad spectrum I have got. Line width at full width at half maximum is 1 hertz. And at 0.55% of the line width, it cannot exceed 13.5 hertz. If it is more than that, your line shape is bad. Not only that, at 0.11% of the height of the satellites, it should be only maximum of 30 times the full width at half maximum. So if the 1 hertz is the line width, full width at half maximum, at 0.11% of the height of the satellites, it cannot be more than 30 hertz. Otherwise, the peak shape is bad. This is a test. Okay, look at this one. I take an example. We have taken a spectrum with 3% CaCl3 in acetone D6. Let us say natural line width is 0.2 hertz. Fantastic resolution. Very good shimming is done. And we got the line width of 0.2 hertz. Then measure the line width of the main peak at the height of the satellites. What did I say? It should be 13.5 times. Multiply this by 13.5 times. This line width at 0.5% should not be more than 2.7 hertz. If it is more than 2.7 hertz, your line shape is bad. Again, increase further. Measure at 0.11% of this height. It cannot exceed 6 hertz because your natural line width is 0.2 hertz. So natural line width tells you about resolution, but the peak width at 0.55% of the CaCl3 peak at the satellite height and 0.11% of that will decide about your shape of the peak. If these conditions are not matched, then your line shape is perfect and resolution is very good. Remember, after doing all our data acquisition and processing, you must ensure you get a very good quality spectrum, very good quality line shape. And if the shapes are distorted, you get multiplicity by because of inhomogeneity, etc. You try to interpret as the multiplicity instead of understanding it is inhomogeneity. Okay. So we have to be very careful before starting an experiment. You always ensure the line shape is perfect and resolution is very good. And afterwards, you have to start your experiment. Now, this is a real peak. Look at this one. CaCl3, 3% in acetone. This is the peak width at full width at half maximum at 50% of the height of the peak. And enlarge it high at the height of the satellite, 0.55% of the peak height. You must see this. 0.11% of the peak height, you will see this one. Okay. In fact, if you really go by the number, 0.55% is wrong. Okay, 50% is 0.5. 0.55 is wrong. It should be 0.055. The 1%, 1%, half of 1% is 0.05. There is a mistake here. So it should be 0.055, 0.5% and 0.011%. But this is a small error. But anyway, it is a unintentional error which you can understand. Nobody will believe 0.55% is lower than 50%. That is 0.5. Let's say it's a mistake. But remember, it is 0.055 at the height of the satellite. This is 0.11% of this one. So these are the conditions you have to match. Then you know peak shape is good. It's a very good shape you got, and the resolution is very good. So these are some processing techniques which I told you you need to adapt while doing your experiment. So I will stop today at this, and in the next class I'll give you something about NMR instrumentation parts, which is very important to know, and then we'll go to some other topic later.